Hey guys, welcome to another exciting episode of, I don't know what to call these things, these videos I make for you. Anyways, I hope they help. This last part of chapter 12, kinetics, we should look at how temperature affects the reaction rate, or specifically the rate constant. And the dude that first figured this out, his name was Arrhenius, very famous Nobel Prize, I believe Swedish chemist, physicist, scientist. Here's his equation. The constant K that we know and love, the rate equals some constant K times the concentration, etc. That's this K. This is a constant, not to be confused with some generic species of some kind, which we have to say we often use A for some generic thing. But this is actually a constant. R is the gas constant that we use on occasion. This one has units of energy in joules, and T is the Kelvin temperature. And EA, so far, we haven't talked a whole lot about. It's the activation energy, the energy needed to get the reaction going. Interesting. Another famous or common rearrangement of that is to take the natural logarithm of this side and the natural logarithm of this side, and you get something like this. The natural logarithm of the e to the x cancels this one out, and I have this constant. No, that's not a constant. That's a variable. That's a constant. Temperature is also a variable. Anyways, this A is a constant. But unless we know what A is, it's a little bit tricky to get a handle on. But it gives us, this equation gives me some kind of an idea about how I might graph temperature versus the rate constant in order to get a linear proportional connection. Here's a graph straight up of some particular temperature constant relationships. So on the x-axis we have temperature, Kelvin temperature. On the y-axis the constant. And of course as the temperature grows larger, the constant gets also grows larger and the rate increases. Most reactions go faster as the temperature gets larger. But I was worried when I first saw that because I can't make any sense of that. I need some kind of mathematical description of that line. So to do that, here's the trick. This was hinted to me when I saw that equation above. But the trick is this. Take the constants and their associated temperatures, or vice versa. You make sure this is in kelvins. You take the reciprocal of the Kelvin temperature and the natural logarithm of the constant. And so here are some new numbers. By the way, the natural log and the reciprocal of t, they are hinted at right here. Natural log of k, 1 over t. Interesting. So when I graph that, this goes on the y-axis, this goes on the x-axis. I get a form very, very similar to y equals mx plus b, the slope-intercept form of the equation of a straight line. And so lo and behold, there's the y, there's the m, the slope of the line, the x-axis is reciprocal temperature, and b is a constant. It's the intercept. Well, it's not constant over many reactions, but in any case, for this particular blah blah, if I really took that data, take this data on this graph, or I should say in a linear regression, here's what I get. I found the slope of the y equals mx plus b on the calculator to give me this, the slope, negative 14,444. The t is the Kelvin temperature, the reciprocal. This is the y-intercept, in other words, the natural log of this constant. So in a way, this is a way to find the constant, isn't it? If I knew the temperature, if I knew this, and I knew how the constants changed, then I could easily solve for A. In any case, the really important thing is this. The slope of this line of the ln of k versus 1 over t, I could call this an Arrhenius plot. And this gives me the slope of the line, which then, since I know this constant, I can find the activation energy. So if I take this slope and basically multiply it times 8.31 joules, I can find the activation energy in joules, but it's usually much more convenient to write it in kilojoules. 3 sig figs, 120 kilojoules. Interesting. This is a method, a mathematical graphical analysis for finding the activation energy, where before we really had no way of finding the activation energy for a particular reaction. Another arrangement of that, and assuming that holds, so here's the similar graph. I'm just generalizing here though. Natural log of A, the constant A, no concentration, just a constant. Intercept, Y equals mx plus B. I could call this, I'm sorry, rewind that last sentence. I call this the 2-point form of the Arrhenius equation. So what if I just had 2 points along the line, this red point and this red point? Would it still work? And the answer is yeah, assuming that linearity to be true, assuming the relationship holds always, then I can just use 2 points, temperature and rate constant points, and I can use this. This is easy to derive from the general Arrhenius equation, comparing point 1 and point 2, property of logarithms and such. And the nice thing is this gets rid of that A factor, that A term. So yeah, that allows me to find the activation energy from point 1, T1, K1, and point 2, T2, K2. It's nice to be careful with this. Sometimes the equation will appear with a negative here in this form, or switch those two around and the negative cancels. And so, I don't know. You'll be given probably this equation on the second exam, maybe even on the final. But it's good to practice a little bit and see if we can make heads or tails of it. This is the same. No, it's not. Is this different data? Oh, forgive me for not looking right now. Let's just look at the data. This is the temperature, 600, 625, 650. So I'm increasing the temperature. What happens to the constant as the temperature goes up? Oh, it also goes up. That makes sense because the rate must also increase along with the constant. Let's see. What else? Oh, yeah. Let's ask the question, if I had this data, what would be the value of the rate constant? What is K at a slightly warmer temperature? Let's call it 765 Kelvin. So I just made that up, honestly, but if it works, it works. If you have the constants, you can plug them in and see what the prediction would be from the Arrhenius equation. So if I jack this up to from 700 to 765, how will this increase? Well, I'll bet it's going to be more than 20, but how much more than 20 is the question. I said, well, let me just take one of these. Let me call this T1, K1, and I'll call this T2, but I don't know K2 in that 2-point form of the Arrhenius equation. So, let's see, T1 was 700 Kelvin, T2 is 765 Kelvin. This one goes with the unknown constant, but my known constant for the 700 Kelvin, here's a finer point also. If this, oh yeah, this was the data from above. If my activation energy was determined to be 120 kilojoules, I need to make sure this gas constant is in the same units. It's usually 8.31 joules, blah, blah, blah. I think it's joules per mole Kelvin. But if we have this in kilojoules, let's have this in kilojoules as well, so they cancel, so they match up. Or I could call this 120,000 joules, and this is 8.31 joules. Whichever way you look at it. Take the reciprocal of this, subtract the reciprocal of that, multiply. I get 1.753, but that's this over here. So let me take e to the power on this, e to the x on this side, e to the x on this side. The e natural log cancels, and k2 over 21.8 equals e to the 1.753. And then I simply multiply both sides by 21.8. And I found, 125, 126. So the bottom line is, I'm probably going too quickly, but that's the bliss of being able to rewind this silly thing. Yeah, the constant grew quite large, 125, with just 65 degrees temperature change, Kelvin. Let's see. Oops. All right, sorry about that. Thanks for waiting. I had to check something out. Plan a little bit ahead here. There's one more question, and if I have time during this video, I'll go over the answer, but you might want to try it right away. First order decay of N2O5 into something smaller, decaying one reactant into something smaller. some of the nitrogen-oxygen compound. I see as the temperature goes up, I have a constant that also goes up from 0.07 to 3 to 50 to 487. So here are the questions. You can practice these techniques we've been looking at. Oh, a couple things. I got to help you out a little bit. Do we care that it's in Celsius? Maybe we do. Also, these are small numbers. This is really 0.0000000. Wait, let me start over. 0.000000787. This is really 0.0000346. This is really 0.000498. You get the idea. So this is really the small numbers. Find the activation energy for the reaction. And what would the constant be at 50 degrees? Well, I'm going to guess 50 degrees is in between here, so my constant's going to be in between. But who in the world knows where? Between 50 and 487. All right, you should pause the video now if you feel like it, and try to answer these two questions based on those temperature and constant terms, data. But if we're moving on, let me show you how I did it. I've got only 3.5 more minutes. Let's see. Temperature, change to Kelvin. Take the reciprocal. Constant, I just rewrote that. So I need these reciprocal Kelvin temperature data. And this constant, I need the natural logarithm. There we go. The natural logarithm of the constant data. This goes on the x-axis. This goes on the y-axis. Use a graphing calculator or a spreadsheet. And here's what I got. I got the slope of negative 10,711. And so to take the gas constant R times that, I get a big number, 89,000 joules, 89 kilojoules. This would also be helpful in different questions, but we probably won't go there. Again, that's the natural log of the A constant term. So at 50 degrees, what do we have? Well, let me see. At 50 degrees, which is 323 Kelvin, I could imagine that 323 is T2. I don't know this one. I do know this. I don't know, I took some data. The temperature at 338 at a constant of 0.00487. This is in kilojoules. This should be in kilojoules. The math looks exactly the same, or exactly analogous to what we've seen before. Subtract those two reciprocals, multiply by that, divide by that, gives you negative 1.472. That means this number must be bigger than this number. And to get rid of the natural logarithm, take e to the x on this side. E to the x here cancels that out. That goes away. E to the negative 1.472 is 0.2296. And so multiply both sides by 0.00487. And my constant comes out to still a small number, but who in the world could have predicted that to be the case? All right, thanks guys. See you in class. Have a good one.